Welcome to our third lesson on electrostatics. We'll be looking at charging by means of contact today. Now, as the word suggests, there needs to be physical contact between the objects before they will be charged. Now, here we're going to make use of spheres to indicate this transfer of charges. Now, a sphere is just a round shape of metal. It looks pretty much like a small ball that's made up only of metal, which is a good conductor of electricity. That means it will allow electrons, once they've been placed onto the sphere, to spread out evenly over the sphere. Now, in all cases, we're going to place these spheres on insulating stands. Now, insulating stands just means it's going to be having an object at the bottom that's a good insulator, and that will then prevent any charges coming from our sphere to move towards the earth or back up again, because the earth is a good conductor of electricity and is also known as the object which will then receive all excess electrons and will also give to an object if it needs electrons. So we do not want that to happen to our sphere, so we're going to put it on insulating stands to prevent this charge flowing from happening between the earth and the sphere. Now, in this case, we're going to start off by bringing two objects in contact. One has equal amount of positives and negatives. That means it's a neutral compound. The other one, though, has got an excess of negatives and is therefore seen as a negatively charged object. Now, when these two are actually going to come in contact, our electrons is going to be transferred from the object that has an excess to the one that has a shortage. So therefore, it will go from our negative charge to our positive charge. Well, in this case, it's just seen as a neutral object. Now, usually, when this transfer of electrons occur, the transfer of electrons only occur up to a point where there's going to be an equal amount of charge on both spheres afterwards. So that means after these spheres have made contact, they must end up with the same amount of positives and negatives. So they should look like twins at the end. So when they make contact, our object with the excess amount of negatives is going to transfer some of its negatives to the neutral object. The neutral object is going to receive those negatives, going to spread them out evenly among the specific metal sphere, and then our negatively charged object has now lost some, or basically transferred some of its electrons. So at the end, we said they must have the same amount of positives and negatives again. If we look at our initial sphere, it has 2 positives and it's got 4 negatives. If I look at my negatively charged sphere, it's got 2 positives and 4 negatives. So they've got an equal amount of charge now, and that is then the correct way when they actually make contact to end up with is the same amount of charge. But in both cases, these objects are now negatively charged. And if both objects are negatively charged, they will end up repelling each other. So these charges would like to move away as far as possible from each other after they've made contact. And that will always be the situation when charges has come in contact. Before contact, they might attract each other or have no force of attraction or repulsion. But always after they've made contact, they're going to have exactly the same charge, and that's going to mean they won't like to repel each other at the end. Now, there's a few formula that we can make use of in order to go and calculate this new charge. And the formula is Q for charge is equal to Q1 plus Q2, that means our first object, plus our second object's charge, divided by 2, because there was 2 objects that made contact, and that's then going to give us our new charge. But let's say we had 3 objects that we decided to bring close together so that they can make contact and transfer their charges. Then all that will happen is our new charge will be equal to Q1 plus Q2 plus Q3, and then we will divide by 3 because we had 3 objects making contact. Now you would note though that we're going to get the charge of one object, but both objects is going to have this same charge at the end. You can also go and calculate the number of electrons that makes up a charge. And that all what we do with that is we take the charge value and divide it by the charge of an electron. And we know the charge of an electron is negative 1,6 times 10 to the power of negative 19 coulombs. And we just use a small letter q because it's such a small charge compared to our bigger charge, which is indicated with a capital letter Q. Let's go and apply this to an example now. A positive 4 coulomb sphere makes contact with a negative 6 coulomb sphere. What would the new charge on each sphere be? Now remember, once they've made contact, they will end up with exactly the same charge. So let's go and use our formula. Q, which is our new charge, is going to be equal to our Q1 plus our Q2, divide by 2 because I'm having 2 spheres. Now it's always best to put the charge, whether it's positive or negative, in brackets together with the value when you add up your values, so that you do not mix up your charges and get to the wrong answer. So I have positive 4 plus negative 6, that ends up giving me negative 2. Divide that by 2 and gives me a value of negative 1 coulomb. Now negative 1 coulomb is going to be the charge on both my positive 4 and my negative 6. So they have now both changed the charge to exactly the same value, and we said because the charge's sign is also the same, it means that they're going to end up repelling each other after they've made contact. Before contact though, they were attracting each other because it was a positive and a negative charge, but after contact, they'll end up repelling each other. Now let's quickly go and make use of our number of electrons formula just to go and calculate what will be the number of electrons that is made up in negative 1 coulomb of charge. So we'll have our negative 1 at the top, divide by our negative 1,6 times 10 to the power of negative 19, and this gives us a total value of 6,25 times 10 to the power of 18 electrons. So it's quite a big number of electrons that's making up just 1 coulomb of charge. Now in our previous example, we had then 2 objects that had specific charge, but let's say one of them was a neutral object. When we have neutral objects, we'll be using a 0 value in our calculation. So just take that into account whenever you are looking at a neutral charge.